Very good morning. Welcome back.
Good morning, sir.
So we shall start with a new topic today. And so far in Unit 1, we have learnt about what is a fuel cell, how does it work, what are the components, what are the fuels that can be used, how the fuel cells can be classified. In Unit 2, we studied about 5 different types of fuel cells. So now we know what are the components, how the fuel cells work, and what happens if the electrolytes change, and what happens if the operating temperatures change. And so is the case with electrodes. So the next thing is we need to know how to find out the efficiency of a fuel cell, what are the losses associated with the fuel cell, and what are the kinetics associated with the reactions that take place at the electrode electrolyte interface. So that is what we are going to study in module 3 or unit 3. So we learn about different types of efficiencies, different types of losses, how these losses can be overcome, how to make a fuel cell more efficient, and what are the what is the contribution of reaction, what is the role of reactions, how effective or what is the impact of reactions that take place at the electrode electrolyte interface on the performance of the fuel cell. Okay, so to start with, so you are able to see the presentation, right?
Yes, sir.
Okay. Okay, so to start with, let's start with the efficiency. And if you remember in unit 1, so we briefly discussed about how the efficiency of a fuel cell can be calculated. So what is happening in the fuel cell? We supply reactants that are fuel and oxidant. So fuel is supplied at anode, oxidant is supplied at cathode. These reactants are fuel and oxidant take part in a reaction, thereby generating some heat, water, and electricity. Electricity is nothing but the flow of electrons through external circuit. To get a better picture, we considered the energy of the reactants, that is the chemical potential. So that becomes the starting point. So the chemical energy of the fuel is getting converted into electrical energy. So that is the very definition of the fuel cell. So we have to start with the chemical energy. So what are the reactants and what is the reaction that is taking place? The hydrogen, that is fuel, and oxygen, that is oxidant, reacts to form water. So this is the overall reaction based on the reactions that take place at anode and cathode. So if we want to talk about thermodynamics and the reactants and products, this is the reaction which we take into account. So a conventional hydrogen oxygen fuel cell, reactants react to give products, that is water. Along with that, little heat and electricity is generated. So now the starting material, the reactants, that is hydrogen and oxygen, and the chemical potential of these reactants is considered as the starting point. That is the energy that we have in hand. So we need to find out how much energy or what part of this chemical potential or chemical energy is converted into electricity. Is it completely getting converted, or what is happening in between? So what are the different forms? is what we briefly discussed in unit 1. So what was that? The chemical potential is nothing but the enthalpy. So, or the chemical potential, when we talk about chemical potential, the enthalpy, entropy, and Gibbs free energy comes into picture. So, enthalpy can be more or less compared with the calorific value of a fuel or chemical energy of that fuel. So, that consists of two terms, that is Gibbs free energy and entropy. So, this Gibbs free energy is the useful part of the enthalpy. Entropy is the part which cannot be utilized. And also, when we talk about Gibbs free energy, so it is actually the energy that is available to carry out work, useful work, and the work associated with change in temperature and pressure are not taken into account. Okay, what happens if we consider the work due to temperature and pressure as well? So work done because of the change in temperature and change in pressure, if we club that with Gibbs free energy, then that is known as exergy. So overall, I repeat, so enthalpy is exergy combined with entropy. So exergy is the usable part. Again, that consists of the energy available to carry out useful work, energy or work done because of change in temperature and work done because of change in pressure. So if three components are clubbed together, it is known as exergy. However, we are not taking exergy into account. We talk only about the Gibbs free energy. That is the energy that is available to do useful work, neglecting the work done because of change in temperature and pressure. So it is this part of energy that is available in a fuel cell which can be effectively converted into electrical energy. That is what we learned. So let's go a little further and let's try to get better understanding of efficiency. So fuel cells use materials that are usually burnt to release their energy, which is nothing but fuel. And electric energy produced should be compared with the heat produced by burning the fuel. So this is a very vague comparison where we take calorific value into account. Instead, to make it more precise, we can talk in terms of enthalpy. So change in enthalpy of formation, very similar to change in Gibbs free energy of formation, is more precise than calorific value. So as usual, wherever the energy is released, it is represented by negative sign. So the negative sign just indicates that energy is released. So we always have to take the magnitude into account. So delta HF with an over bar indicates that it is molar specific enthalpy of formation. That means per mole of substance. So with that, if you want to calculate the efficiency, so electrical energy produced per mole of fuel with respect to the change in enthalpy of formation per mole is a way that can be considered to find out the efficiency. So to proceed with that, when it comes to this change in enthalpy of formation per mole of substance, depending upon the temperature at which this reaction is taking place and depending upon the physical state of the product, two values are obtained. So let's look at the reaction 1. So it's this. So in this case, it's the same hydrogen and oxygen react to form water. However, water that comes out is in the form of steam. So when that is the case, this delta HF value will be minus 241.83 kilojoule per mole. So here the negative sign just represents that the energy is released. So we have to take the magnitude, that is 241.83 when the water is in the form of steam. That means this reaction is carried out at a temperature beyond 100 degrees centigrade. So another case is the same reaction that is carried out at ambient temperature less than, I would say, close to room temperature, but definitely less than 100 degrees centigrade. So in that case, it's the same reaction, it's the same reactants and products, but the state of the product is in liquid form. In such a case, the delta HF will be minus 285.84. So again, if we take the magnitude, we get a higher value. So this is represented as HHV, or higher heating value, and the other one 241 in the when the water is in the form of steam is considered as LHV, lower heating value. And when nothing is mentioned, it should be considered as LHV. If they do not clearly mention whether the calculation is based on HHV or LHV, it is usually LHV. So now, if we try to figure out what is the maximum possible efficiency of a fuel cell, in that case, we have to take the ratio of the change in Gibbs free energy of formation per mole and change in enthalpy of formation per mole. So this is the maximum available out of that. So this is what can be utilized. So this is how we can calculate the maximum possible efficiency of a fuel cell. So with that, if we just look at the form of water or form of product and operating temperatures, so we can find out what is the maximum voltage that can be obtained, and hence the maximum efficiency, which is known as the efficiency limit. So here, when the temperature is less than 100, here there are readings for two temperatures, 25 and 80. In both cases, the form of product is liquid. So with that, the delta GF value, so keeping aside the negative sign, if we consider the magnitude, so when the operating temperature is 25, the delta GF will be maximum, that is 237.2. So with that, the efficiency will also be maximum, that is 1.23. And efficiency limit, how do we get this? So delta GF by delta HF. So this is the maximum possible efficiency. So now we are just looking at this from the theoretical viewpoint. So on theory, on paper, based on equations, this is what we get. So what happens practically, we shall look into it a little later. So now the clear observation here is, with increase in temperature, the delta GF value decreases. So is the associated EMF and efficiency. So what did we learn so far? It is the Gibbs free energy of formation that can be effectively converted into electricity in a fuel cell. What is the reference? So it is the enthalpy of formation. So in order to find out the maximum efficiency, we have to take these two into account, the ratio of delta GF by delta HF. So with that, as we know that the change in Gibbs energy of formation is completely dependent on temperature, and with increase in temperature, the delta GF decreases. So with that, the maximum voltage as well as the efficiency limit will also decrease. So any questions so far? Is this clear? Shall I proceed? Hope you guys are listening. Okay. Okay. So now when enthalpy comes into picture, and if you want to compare this fuel cell system with other energy generation systems, such as heat engine, so the Carnot efficiency comes into picture. So in case of Carnot efficiency, with increasing operating temperature, the efficiency increases. However, in case of fuel cell, the efficiency of the fuel cell decreases with increase in temperature. But at some point of time, we did learn that there is a possibility to generate additional power by utilizing the waste heat that is coming out of the fuel cell. So in case of fuel cells that are operating at high temperatures, so such as MCFC and SOFC, even PAFC, anything above 100 degrees centigrade, there is a possibility of utilizing the waste heat to generate additional power. So how can that be done? So there are two ways of doing it. One is you use that product gas that is coming out, you exchange heat with that to generate steam, or if you realize that everything that is coming out is water, then that itself can be used as steam. Using that, you run the steam turbine. Additional power is generated. That is one possibility. Another possibility is you operate the entire fuel cell at a higher pressure. Because of that, the gaseous stream that comes out will be at higher pressure. Use that gaseous stream to run a gas turbine and generate additional power with that. So that is the second possibility. There is one more possibility, that is it is combination of a heat engine and a gas turbine. So however, the first two methods where a heat engine is used or a gas turbine is used, there are such examples that are available practically. But the third case, practical examples are little less, where both gas turbines as well as the heat engines are used to generate additional power along with the normal fuel cell operation. So this is how the CHP works. In such a case where there is a possibility to generate additional power by waste heat recovery, the efficiencies will be different. Definitely better than the fuel cell efficiency alone. So here what you see is the trend is decreasing with increasing temperature. So in case of CHP, it will be a straight line. So it is the combination of the heat engine as well as fuel cell, and so it's almost constant irrespective of the operating temperature. Okay, and now whatever we discussed was theoretical efficiencies, but when it comes to the actual efficiency or the efficiency when the fuel cell is under operation, we always compare the working efficiency with the theoretical maximum efficiency. So for that purpose, a reference or benchmark is required. So that benchmark value with respect to voltage that is generated in a fuel cell will be based on one based on HHV, another based on LHV. So 1.48 when HHV is considered, higher heating value is considered, and 1.25 when LHV is considered. This is the benchmark. So that is the maximum efficiency which we learnt just now. So we take that as a reference, and actual efficiency will be compared with this. Means, how do you calculate the actual efficiency? You measure the actual voltage and compare that with the maximum possible voltage. So you get the efficiency. So this 1.48 and 1.25 are the voltages obtained from 100% efficient systems. Actual efficiency is the ratio of actual voltage to maximum. While doing that, there is one more factor that is known as fuel utilization coefficient. So in practical fuel cells under operating conditions, when the fuel is consumed and the electricity is being current is being drawn by an external load, all the fuel that is supplied will not be completely utilized. So only part of it is utilized, or I would say part of it is definitely lost. So taking that into account, a term known as fuel utilization coefficient is coined. So what is this? This is the ratio of mass of fuel reacted in fuel cell, to mass of fuel that is supplied to the fuel cell. So that ratio speaks about how much fuel is utilized, which is termed as fuel utilization coefficient. So with all these, if we try to calculate the efficiency, which is represented as eta, so we take this mu f into account. Vc is the actual voltage that is measured in a fuel cell, that is compared with the maximum possible efficiency in case of HHV, that is 1.48. And if you want to compare that with maximum efficiency, sorry, maximum voltage at LHV, then it will be the other value, that is 1.25. So like that, you will be able to calculate the actual efficiency of the fuel cell. So far in this new topic, or in this unit, what did we learn? We started with the way of calculating efficiency using Gibbs free energy, or I would say the Gibbs free energy was taken into account in order to find out the voltage that is generated in a fuel cell. And later with that, we defined how to calculate the maximum efficiency, which is the ratio of delta GF by delta HF. And when it comes to this delta HF, there are two values. So one is higher heating value, other one is lower heating value. So with that, we were able to find out the maximum possible voltage and maximum possible efficiency, or efficiency limit of a fuel cell. So when we continued with that, we also learned about how to calculate actual efficiency. So here the reference or benchmark is always the maximum voltage. So this efficiency is based on the voltages. So the actual voltage is measured, and that is compared with the maximum EMF, that is maximum voltage. So it is 1.48 for higher heating value and 1.25 for lower heating value. Along with that, the fuel utilization coefficient is also taken into account. So with this, we get the efficiency of a fuel cell. In general, this fuel utilization coefficient mu f is 0.95. Means on an average, around 5% of fuel, only 5% of fuel is getting wasted. So 95% of the fuel is always effectively utilized. So this is one way of calculating efficiency. With this background, we shall also figure out what are the other types of efficiencies that are in use when it comes to fuel cells. So four different voltages. One is intrinsic maximum efficiency, voltaic efficiency, Faradic efficiency, and the overall efficiency. The overall efficiency is the other three clubbed together. So that is the intrinsic maximum, voltaic, and Faradic efficiencies clubbed together. we get the overall efficiency. So these are certain terms that are associated with fuel cells. However, practically, you may not get to see all these types of efficiencies, or all these types of efficiencies are not frequently used everywhere. So, but this is just for your information. So, different possible types of efficiencies. So, to start with, let's speak about intrinsic maximum efficiency. So, before categorizing the efficiencies, how did we define the efficiency of a fuel cell? By considering delta G by delta H. So here a specific name is given to that, which is intrinsic maximum efficiency. So we are essentially discussing the same thing, that is delta G by delta H. Now we clearly know that delta H is delta G plus T delta S, or I would say enthalpy is sum of Gibbs free energy and the product of temperature and entropy. So H is G plus Ts, and if you want to calculate G using that equation, so if you just rearrange, it becomes G equals to H minus Ts. And we always take the change into account. So in the equation delta G by delta H, if we replace delta G with delta H minus T delta S, so we get this form. So how did we get this? This part delta G was replaced with delta H minus T delta S. So in that case, we get this equation. So what happens here? This equation delta G minus T delta S reinforces the observation of decrease in Gibbs free energy with increase in temperature. So in these three terms, the enthalpy, Gibbs free energy, and entropy, the enthalpy and entropy are not as sensitive as Gibbs free energy with respect to temperature. I repeat this statement. So when we consider these three terms, enthalpy, entropy, and Gibbs free energy, the terms enthalpy and entropy are not as sensitive as Gibbs free energy with respect to temperature. So even though there is variation, it is minor, so it can be considered as constant value. However, with increase in temperature, we clearly know that the Gibbs free energy will decrease. Okay, so in this equation delta G minus T delta S, so delta G is decreasing, and the other part of the equation, the T delta S is increasing because of increase in temperature. So that means the usable form of energy, or the energy that is getting converted into electricity, is decreased with increase in temperature. So that is a justification for what we observed. Okay, so temperature is rising, because of that T delta S part is increasing. So that means the energy that is getting converted into heat is increasing, and the energy that is getting converted into electricity is decreasing. Any doubts in this regard? So we started with defining the efficiency, the maximum efficiency, and we learned we defined different types of efficiencies, that is intrinsic maximum, Voltaic, Faraday. Now we are starting with intrinsic maximum, which is nothing but the efficiency calculation of a fuel cell with which we started. So here we are just making use of the relation between G, H and S, and with that, this is what we obtain 1 minus T delta S by delta H. There are instances where the delta S is negative. According to thermodynamics, depending upon certain equations, there are examples where delta S is negative. In such a case, so this entire term, because of the negative delta S, becomes positive in this equation. So because of this, theoretically, the efficiency may exceed 100%. So whether this is practically possible? No. But on paper, according to the equation and thermodynamics, in cases where the entropy can be negative, the change in entropy can be negative for a reaction. In such case, theoretically, the efficiency may exceed 100%. So this is for your information. This is about the intrinsic maximum efficiency. So the next form is the voltaic efficiency, a slight variant. So where the efficiency is purely based on the voltages. So that is the cell voltage, the measure voltage, and thermodynamic reversible voltage. We are not taking the fuel utilization coefficient into account, and this is defined as voltaic efficiency. This kind of efficiency varies between zero point 0.9 and 1. So this is on an average usually. That's how it will be. So third variant is Faraday efficiency. Here the efficiency is calculated based on the current, that is uh, measured, or the current that is obtained in a fuel cell and the maximum possible current. If you take the ratio of the two, so we get an efficiency, and that is defined as Faraday efficiency. So if we club these three, we get the overall efficiency. So EI, intrinsic maximum efficiency, EE, that is voltaic efficiency, EF, Faraday efficiency. So all these three are clubbed together, and the overall efficiency is found out. So however, this is the categorization just on paper. It's theoretical categorization. Practical efficiency, it could be just based on the voltage that is drawn and the maximum possible voltage combined with fuel utilization coefficient. So that is the most commonly used efficiency calculation. So this is about types of efficiencies. So now we have learned about efficiency. The next thing that we need to learn is the losses that are associated. So we realized there are many times we discussed that the practical voltages are much less than the theoretical value, or reversible open circuit voltage, or no loss voltage, but we never discussed about the reasons for that decrease in actual voltage. So in one case we briefly touched upon the names, that is the activation loss, and another case was ohmic loss, but these losses we are going to discuss in detail. Before that, we shall try to define these terms. uh, this loss is also defined as polarization, over potential, over voltage. So these are different terms used for the same thing. So if we take the example of activation, it can be called as activation loss, activation over potential, activation over voltage, or activation polarization, or active. So these are the different terms that are used for the same thing. And Now with that, we shall try to get a better understanding of these losses. And in all the fuel cells, irrespective of the type and application, the characteristics of a fuel cell is determined using IV curve, known as IV characteristics. So I is current, V is voltage. So current voltage characteristics, abbreviated as IV characteristics, is commonly used irrespective of type of fuel cell. So what is this? A plot of cell voltage versus current density is known as IV curve. So this IV curve is part of this characterization of a fuel cell and part of IV characteristics. So what is happening here? A fuel cell is under operation. The current that is being drawn from the fuel cell is varied, and the effect of that on the change in voltage is observed. So there are instances where the axes are swapped, meaning the current density is plotted on y-axis and cell voltage is plotted on x-axis. That is because when it comes to these characterizations, which we are going to learn in detail in unit 4, there are two ways of doing it. That is, you vary or control the voltage and you measure the effect on current. The other one is vice versa. You control the current and the impact on voltage is measured. So because of this, these values are used on x and y axis interchangeably. So in this case, so the general convention, the cell voltage is used on y axis, current density is used on x axis. So what is done here? The current is controlled and the corresponding voltage is measured. So the current that is being drawn out of the fuel cell is increased and its effect on voltage is measured. Okay. So here there is a line parallel to x-axis at an voltage of 1.2, which is listed as no loss voltage. So which is nothing but reversible open circuit voltage on paper, that is theoretical no loss voltage. So using a HHV or LHV or at a temperature, you will find out what is the no loss voltage. So that is delta GF minus delta GF by ZF. So with that, depending upon the operating temperature, you get a value. So that is the no loss voltage 1.2 here for a fuel cell that is operated below 100 degrees centigrade. However, when a load is connected to the fuel cell and you have switched on the fuel cell, but no current is being drawn, the load is just connected, but the current is not being drawn out of the fuel cell. In such a case, even when the current drawn is zero, the voltage that is measured is not the same as the theoretical no loss voltage. So instead of 1.2, it is close to 1.01 or 02. So 1.2 is the no loss voltage and 1.02 is the actual voltage that is measured. So the fuel cell is turned on, switched on, and is in operation. It is in working condition. Load is connected. However, the load is not yet drawing the current. In spite of that, there is a drop in voltage. It is not the same as the no loss voltage. that could be because of a certain loss, and we are going to study that loss soon. Later, the current is being slowly drawn from the fuel cell. With that, the voltage in this region so decreases non-linearly drastically. After certain point, until this point, the loss in voltage or the decrease in voltage is fairly linear, and again at very high current densities the drop in voltage is again non-linear. So that means this IV curve can be split into three zones. That is zone 1 from 0 till this point. This is zone 2 from this point till this point, and this is zone 3. So these three zones talk about different types of losses that are associated with the fuel cell. We shall go to those losses at a later stage. Now we are just trying to understand a basic IV curve. And this is an IV curve for a fuel cell operating at a temperature below 100 degrees centigrade. So what are the observations? E is about 1.2 for a cell operating below 100 degrees centigrade, which is the no loss voltage. The voltage obtained from a working fuel cell is considerably less than 1.2. Even the open circuit voltage is less than the theoretical value. There is a rapid initial fall in voltage, and in the second zone voltage falls less rapidly and linearly, and in third case at high current density again there is non-linear voltage drop. These are the observations based on this IV curve. Now let us look at another IV curve obtained by operating a fuel cell at a higher temperature. So here this is an example of a fuel cell which is operated above 600 degrees centigrade, close to 800 degrees centigrade. So in such a case, the first observation is the no loss voltage value is 1. Why is this? That is because with increase in temperature, the Gibbs free energy, change in Gibbs free energy of formation per mole decreases. Because of that, this no loss voltage value will also decrease. Okay, so that is the first observation. Second observation is, even though the no loss voltage is of lower value, the initial loss is less when you operate the fuel cell at a higher temperature. That means the difference between the actual open circuit voltage and the theoretical open circuit voltage is minor, trivial in case of fuel cell operating at a higher temperature. So again, from that point onwards, in the second zone, the drop in voltage is fairly linear, and again in third zone, it is again non-linear. So what is the difference? One is the no loss voltage is less, and the loss in zone 1, the difference between the actual open circuit voltage and theoretical open circuit voltage is less in case of fuel cells. See, OCV is only a little less than the theoretical value. The initial fall in voltage is very small, and the graph is more linear. And operating voltage is generally higher as voltage drop is smaller at higher temperatures. So if you compare these operating voltages with that of fuel cells that are operated to temperatures close to room temperature or less than 100 degrees centigrade, operating voltages are generally high. That is because the loss is less. This is how you compare the IV curves of fuel cells operating at temperature less than 100 and more than 100 at very high temperatures. So now we understood how to interpret an IV curve, what information can be extracted from an IV curve, and how it is plotted. So this is again the table which I had seen earlier. With that, we may have to define and learn more about the losses. So as I mentioned earlier, there are many commonly used names for this potential difference or voltage difference. So one is over potential or over voltage, polarization, irreversibility, losses, and voltage drop. All these things mean the same. And let's stop here today. In the next class, we shall continue with getting more information about the different types of losses. So any questions so far? People already started leaving. Okay, so if no questions, we shall continue in the next class. And so far we do not really know about when is the internals going to be. So whenever I get to hear about the internals, I will pass on the same information to you. So but be prepared. So you continue the preparation. So all the study material is available, and I have added the presentations as well on the Google Classroom. So you might have got a reminder email regarding that by now. So kindly make use of that. So if there is anyone who has still not joined the Google Classroom, kindly do so. And we shall continue the discussion in the next class. Thank you.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.